So good evening, everyone. To the Vigyan Adda welcome to the Vigyan Adda talk today. Today it's a great pleasure to have Dr. Sthitadhi Roy with us as the speaker. Professor Sthitadhi Roy is a theoretical physicist at the International Center for Theoretical Sciences, Bengaluru, who works at the interface of quantum condensed matter and statistical physics. His current research interests revolve around the out of equilibrium dynamics of quantum many-body systems, with a certain focus on disordered systems and quantum entanglement. Sthitadhi obtained his undergraduate degree, MSc Integrated, from IIT Kanpur in 2013 and pursued his doctoral research at the Max Planck Institute for Physics of Complex Systems, Dresden, Germany, where he finished his PhD in 2017. Before joining ICTS, he spent a little over 4 years at the University of Oxford. So, and today he's going to talk about dynamics of quantum entanglement. We really look forward, Sthitadhi, to this talk. Over to you.
Thank you, Rukmini, for the very kind and generous introduction. And let me also start by thanking the outreach team of ICTS-TIFR for sort of having this wonderful series of Vigyan Adda talks. And I think it's a great opportunity for us to communicate what we do in a sort of slightly simpler language to a broader audience, and it's really a pleasure for me to give this talk. So, as Rukmini said, that a large part of my research interests do revolve around out of equilibrium quantum systems, and what I'm going to talk about today is the dynamics of quantum entanglement. And as it happens, because I spend a lot of time thinking about dynamics of quantum systems, and entanglement happens to be and sort of almost the defining property of quantum systems, you cannot really escape thinking about the dynamics of quantum entanglement. And that's what I'm going to talk about today. And okay, so basically with that general introduction to the talk, let me actually start with the actual talk. So let's go back to times when we didn't know anything about quantum mechanics, and we didn't know about quantum entanglement. And if someone said the word entanglement, then one of the things at least that would have come to my mind is my headphones getting all jumbled up together every time I put them in my pocket. And we would say that the wires of my headphones have gotten entangled, just like a picture here. But what that actually means in plain English is that if you want to extract each end of your headphone, then it becomes very difficult or sometimes impossible. Quantum entanglement, mysterious as it may sound, is not very different from that, okay? Because suppose I have a whole bunch of different systems here, each sort of gray patch, think of it as some quantum system. And if I say that they are all quantum entangled with each other, meaning that there is something non-trivial that binds, it becomes something more. It becomes something more complicated, something more correlated. And another way of saying that is each part of the system actually has some information about every other part of the system. So somehow the entanglement, you can think of entanglement as some sort of a web of correlations between different parts of the system, in a way that the information of a given single part is not just contained in that single part, but it's shared all over the system. And that's probably one of the sort of simplest and vivid ways of thinking about quantum entanglement. So of course, what I'll try to do in this talk is try to motivate that why quantum entanglement has to be. I mean, why quantum entanglement is there, and you cannot really escape the fact that something like quantum entanglement exists. I'll try to put some of those ideas, or some of the ideas of how to quantify entanglement on some sort of a mathematical footing. Of course, I'll not go into great details because this is a talk for a broad audience. And then I'll talk about how things typically, or how the entanglement typically changes when quantum systems undergo some time evolution. Okay. So now, since for the rest of the talk, we will be talking about quantum systems, I think it's useful to build a little bit of vocabulary and the language that we will be using. So let's do a very quick 5-minute, 2-slide crash course on all the quantum mechanics that we will need in this talk. So the title of this talk is, or the title of this slide rather, is From Bit to Qubit. Now, from here, what I'd like to motivate is the idea of a quantum bit, because that's something we will be using through the rest of the talk. Now, before we go to a quantum bit or a qubit, let's think about a classical bit. Something that all our computers, all our mobile phones, all the electronic devices, we have all of them run on classical bits, right? In the sense that a classical bit, you can think of it as some quantity which has two possibilities. It's either 0 or 1. In an electronic language, it might mean that it's something is on or something is off, and that's how almost all of our electronics are controlled. Now, let's slightly take a quantum mechanical language and say that one of the simplest quantum degrees of freedom you can think of are electrons, and electrons have a property called spin. Now, this spin can either be up or down. So think of this spin as something like an arrow, which either points up, in which case it corresponds to 1, or it points down, in which case it corresponds to 0. So far, all of this is classical. But one of the most important pillars of quantum mechanics is the idea that you can have coherent superposition. And this is, we call it the principle of superposition. What that means is that a qubit or a quantum object does not have to be in one of the two classical states possible. In this case, 2, because I'm talking about a bit. It can be in principle, it can be many. But the point is that it does not have to be in one of the classical states possible. It can actually be in a superposition. And this is a coherent superposition, meaning that the C up and C down, they are not necessarily just some real numbers. They can actually be complex numbers, and they carry an information of a magnitude, as well as carry the information of some phase. And that's where the coherence comes from. Now, mathematically speaking, if I give you a state and when I write it with this angular brackets, all I'm meaning is that this is my definition of a quantum state. Okay. But a quantum state, notice that in order to define a quantum state of this qubit, what I need is basically two complex numbers. Of course, they are not completely unrelated, because the state has to be normalized in the sense that the probability of finding the qubit to be in either the up state or the down state should sum up to 1. So that imposes some constraint on the two numbers I have. But nevertheless, the central point is that I can write the state in terms of two complex numbers. And of course, if I have two numbers, I can arrange them in the form of a vector exactly in this fashion. So this is how we will be thinking about quantum mechanical states in this talk. So this is how we write a quantum state, and this is basically the principle of superposition. Another important facet of quantum mechanics, and this is again something that many of you might have heard about, is the fact that in order to know what state the system is in, you have to make a measurement. But a quantum measurement, unlike a classical measurement, actually goes and disturbs the system. The process of measurement actually changes the state of the system. And this is again a property of quantum mechanics that makes it fundamentally different from classical mechanics. So now suppose I have a state which is a coherent superposition. So whenever I draw a picture like this, I don't mean that there are two qubits here. I mean that there is one qubit here, which is a superposition of the two states in this fashion. Now, suppose I go and measure the spin. Okay, I have some apparatus, I have some measurement meter, and I ask that, tell me if my spin is up or if my spin is down. So what ends up happening is that with some probability, which is C down square, I'm going to get the spin to be down. With some probability C up square, I'm going to get it up. Okay, and this is again the probabilistic nature of quantum mechanics at play, and the fact that the state of the spin went from this coherent superposition here to something which looks like a classical state here is basically what we often call the collapse of the state. That the state was in some superposition of two states, you did a measurement and it collapsed into one of the two states possible in this case, and the two possibilities have their own probabilities. Okay, so then let me move on to another final bit of information that we will need to understand almost all of this talk, which is the idea of density matrices. So what I just now said, that I can write down a quantum state in this fashion. These C up and C downs are complex numbers, so we call them probability amplitudes, and the modulus squared of these numbers are basically what the probabilities are. So from a probability amplitudes to go to probabilities, you basically mod square them. And I said that you can write down the quantum state as a vector in this fashion. But of course, you can also write down a conjugate of the vector. So all you do is you take this column vector and you write it as a row vector with the entries complex conjugated. Now, then what you can do is you can define a matrix, okay, by taking this state here and multiplying it with its conjugate here. So this is a column vector, this is a row vector. If you try to multiply them in this fashion, the basic principles of linear algebra tell you that you are going to get a 2 by 2 matrix here. If you do the computation, this is what comes out. Now notice that the diagonal entries of this matrix are nothing but the original probabilities we had, not the probability amplitudes, but the actual probabilities. So the basic understanding is that these diagonal entries, the ones that are encircled in blue, give you classical probabilities, and these red circles, they actually carry the information of the quantum coherences. Okay, that's where actually the quantum nature of the state is hidden, because the C up square and C down squares are simply the classical probabilities of finding the state in one of the two configurations, up or down. Okay, so what we did in the last 5 minutes or 4 minutes was we introduced the notion of quantum state. We introduced the notion of, and we said that we can write it as a vector. What I said was there is exactly an equivalent way of writing the state in terms of a matrix. And I talked about measurement and collapse. Namely, if I try to measure a quantum state, it goes to one of the classical states possible with its associated probability. Okay, so, and I think that's all the quantum mechanics that we will need to understand this talk. So with that out of the way, let me try to start talking about entanglement. Now it's just fair that if I'm going to talk about entanglement, I might as well start from the very beginning and give you a small sort of historical picture of how entanglement came to be. So the earliest mention of entanglement in physics literature, possibly, this is of course slightly questionable, is in a paper that came out in November 1935 by Erwin Schrödinger. Erwin Schrödinger is one of the sort of founding figures of quantum mechanics in the form that we today know. And he wrote a paper in German, which the title of which translates to The Current Situation in Quantum Mechanics. Now, I'll talk a bit more about the current situation and what does the current situation back in 1935 meant. But you see, he says something here, which is quite interesting. He says that thus one disposes provisionally until the entanglement is resolved by actual observation of only a common description of the two in the space of higher dimensions. So this two is basically two quantum mechanical objects. Like, we had in the first slide, we had many quantum mechanical objects. Here he sort of simplifies matters and says that there are two. And he says that individual or knowledge of individual systems can decline to the scantiest, even to zero, while that of the combined system remains continually maximal. So this is exactly what I was saying in the first slide, that each part of the system may not have any information at all, or the information that it has is very little. What you need is, you need the description, or you need the information about the whole system to describe the state. And then he goes on to say that this is what keeps coming back to haunt us. Of course, he says this because back in 1935, the notion of quantum entanglement was extremely debatable, and there I use the word spooky. So why did I use the word spooky? Because Albert Einstein quite famously called this reportedly as spooky action at a distance, and he didn't like the notion of entanglement. In fact, Albert Einstein, as many of you again might know, didn't really like quantum mechanics. He had this series of extended debates with another great physicist, Niels Bohr, who also is one of the sort of founding fathers of quantum mechanics. And Albert Einstein was very, very uncomfortable with the idea of this probabilistic interpretation of the nature that's around us, which quantum mechanics was sort of forcing on us. In fact, many of you know that in some version, he told Niels Bohr that he didn't like quantum mechanics because he felt that God or nature should not be playing dice. So that was one of the reasons why Albert Einstein did not like quantum mechanics. In fact, there was another reason why he did not like quantum mechanics, because Albert Einstein, Boris Podolsky, and Nathan Rosen, the three of them, together wrote a paper where they were actually questioning whether the quantum mechanical description of the nature around us is really complete. And Okay, so you notice that this paper came out in the May of 1935. And Schrodinger's paper came out in November 1935. So in a way, Schrodinger's paper was sort of a comment on what Albert Einstein, Boris Podolsky, and Nathan Rosen were trying to say. And also the views of Einstein, Podolsky, and Rosen were debated by Niels Bohr. But the point is that, this notion of quantum entanglement already was, people realized that this is an extremely important development, understanding quantum entanglement. Does it even exist? If it exists, what does it mean for how we perceive nature and so on? In fact, again, not to sort of put a too serious point on it, this was important enough that this actually made it to in a very tabloid fashion to the New York Times. And in fact, you notice that this actually came out before the actual paper got published. Okay, so what was the main concern that Einstein, Podolsky, and Rosen had? What they were saying came to be known as the EPR paradox. EPR is Einstein, Podolsky, and Rosen. So what they're saying is, imagine I have two qubits, which are really far away in, maybe one is here and another is on a different planet. And let's say that they are in a state which is something like this. So there is a classical configuration which is up down, and there is another classical configuration which is down up. And what they are saying is that, of course, this is a valid state to write. Now, suppose I write this state and I say that these two qubits, which are arbitrarily far away, live in this particular state. Then you go and do a measurement on this particular qubit, okay, on the second qubit. Now, as we discussed, the second qubit either returns an outcome which is down or it returns an outcome which is up. But if the second qubit returns an outcome down, then you are basically forcing the first qubit to also be up. So by measuring just the second qubit, you seem to have gotten the information of also the first qubit, and in a way you have forced the first qubit into some particular state. And it's the other way around as well, that if you, upon measuring the second qubit, you actually get an up state, then it seems like that you have gotten the first qubit in a down state. And this is something that did not sit well with Albert Einstein, because, as I'm saying, measuring one qubit immediately reveals the state of the other and possibly affects the state as well. And the crucial word here is immediately. And what this means is that even if these two qubits are arbitrarily far away, you could, in principle, do something almost instantaneously. And this was not quite compatible with Einstein's theory of relativity, because Einstein's theory of relativity says that nothing can travel faster than the speed of light. No information or no signal can travel faster than the speed of light. So, but here what we are saying is that, well, we have two qubits which are in an entangled state. They are arbitrarily far away from each other. And I do a measurement on one of the qubits, it immediately affects the state of the other qubit, or it immediately tells me some information about the state of the other qubit. And this is something that's not quite compatible with theory of relativity. So Einstein, Podolsky, and Rosen, they were questioning this very notion of entanglement. And what they were suggesting was what eventually came to be known as local hidden variable theory. So what they were saying was that the notion of quantum mechanics, as we know, is not complete. Each qubit actually carries some extra information. Okay, this extra information is something that we will never get to know. That's why this is a hidden variable. So, for example, let that information in the first qubit be blue, and let that information in the second qubit be orange. And these hidden variables, which we as observers will never be able to see or never be able to calculate, is what carries the information of the measurement results. And they carry this result even before the measurements are made. So this was all nice for Einstein because it got rid of the probabilistic nature of quantum mechanics. And it also sort of explained that why, even before I made the measurement, the outcomes were in a way already fixed. So then, there is no problem that yes, the information of one spin actually traveled faster than the speed of light, or traveled instantaneously from one qubit to the other qubit. Okay. So a sort of very loose analogy for this is to say that suppose, you have a pair of gloves, and I put one pair, I put the left glove in one box and I put the right glove in another box. and I send these two boxes to some very far away locations. Now, if one person opens the box with the right glove, he sees that he has the right glove. So he immediately knows that the other person has the left glove. But that's basically all because, there is this idea that I started off with a pair of gloves. And that's a loose analogy for this hidden variable type theory. Okay, so this was one way in which Einstein, Podolsky, and Rosen tried to say that there is nothing called quantum entanglement, to put it very strongly. They were questioning this notion of entanglement, and they said that the entire description of quantum mechanics is not complete. There are these extra hidden variables which control what we are basically seeing here. Okay, so then this happened in 1935. Niels Bohr, of course, had some objections to this, but the objections to this local hidden variable type theory were not made very, very concrete until this person named John Stuart Bell came up with his ideas in 1964. So 1964, in a way, so you can sort of say that 1920s and 30s were basically the time, late 20s and 30s were basically the time when a huge amount of development happened in quantum mechanics. And then, there was a bit of a lull where there were lots of open ends, and things were not, lots of things were unclear. And then the next huge development in quantum mechanics happened in 1964 due to this person called John Stuart Bell. So what he said was, okay, let me assume that EPR's local hidden variable theory is correct. So he put it on more formal grounds. So he, of course, said that let's consider these hidden variables which carry the information of the measurement results even before the measurements are made. He also put in this condition that this local or these hidden variables are local, in the sense that what these hidden variables do, they can only affect other degrees of freedom which are nearby. They cannot suddenly affect things which are very far away in space. And he also made another point that whichever way the hidden variables show up, that's basically independent of what apparatus you are using to measure your quantum degree of freedom. This is basically a restatement of the fact that the measurements have already been fixed, or the outcomes have already been fixed even before you have made the measurement. Okay, so he put these things on very formal mathematical grounds. And what he said was, if these points were to be correct, then you have some very strong constraints on the correlations between the measurement results that you would get between the two qubits. So he took this view that let's say this hidden variable theory is correct, then I can do sort of different kinds of measurements on each of the two qubits. And then if I actually put these ideas on a mathematical footing, then the measurements between the two qubits are going to be very strongly correlated with each other. And those correlations must satisfy some constraints. They must satisfy some conditions. Okay. And those are called, or those in today's world, we know them as Bell's inequalities. But then Bell went and showed that if you actually take a state, which is a quantum mechanical state, then, and if you do the same set of measurements which give you the Bell's inequalities on that, then these correlations actually violate the inequalities. There is no way that those inequalities are consistent with quantum measurements. And this was the first sort of concrete demonstration that the local hidden variable theory is very likely incorrect, and quantum entanglement is what is there in reality. So now, of course, I really like to describe Bell's inequalities and how he put them forward in some detail, but that's, I think, beyond the scope of this particular talk. So what I'll try to do is I'll give a very, and more importantly, because those are quantum mechanical calculations, I cannot draw very nice pictures for them, because as I said, quantum mechanics is probabilistic. So I'll basically have to draw lots and lots of pictures. So what I'll do is I'll give you a very loose analogy for Bell's inequalities. Okay. So it's a classical analogy, but it kind of is in the spirit of what Bell was trying to say. And if you understand this analogy, maybe if those of you are interested, if you go back and actually try to read the mathematical foundations of Bell's inequalities, you'll probably appreciate them quite well. So the game is as follows. So we have two characters. Let's call them Alice and Bob. And these are sort of standard names used in the quantum information literature. I think my understanding is that before people got creative, they called them A and B, and then eventually they came up with names Alice and Bob. So the idea is that both of them have a box of their own. So Alice has a blue box and Bob has a green box. And each box has a slot in which they can push some money. And when they push some money into the box, then some toy comes out. Okay, so each box can produce a toy car or a toy doll. That's what these setup is. These boxes are in no way connected to each other. Okay, these boxes cannot communicate with each other. There is no mechanical or otherwise coupling between these two boxes. So that's the setup. And the rules of the game are as follows. So if Alice puts a 1 rupee coin in her box, she gets a car. She gets a toy car. Okay. If Alice puts a 2 rupee coin in her box and Bob also puts a 2 rupee coin in his box, then it produces a car and a doll, but in any order. The order is not important. And the third rule is that any other combination produces necessarily either 2 cars or 2 dolls. Now, of course, what has happened here is that I have made up this, or not me, but two physicists named Sandu Popescu and Rolik. They actually made up these rules quite carefully because they were trying to give an analogy of the kind of rules that quantum mechanics imposes on the measurement outcomes. So really think of this this pushing a coin as doing some measurement and getting a toy car or a toy doll as some outcome of that measurement. And of course, quantum mechanics imposes some restrictions on what kind of outcomes can come out depending on what kind of measurements you do. And these sets of rules, or this set of rules, is basically mimicking those exactly. Okay. So now let's see. Now that we know the setup, now that we have our toys, we have the rules of the game, let's actually try to play the game. So here are the possibilities that Alice can put a 1 rupee coin or a 2 rupee coin. Bob can also put a 1 rupee coin or a 2 rupee coin, and there are other boxes. So let's start with Alice putting in a 1 rupee coin in her box. So remember that this is a single instance of the game. Okay. So I'm basically looking at a single instance of the game. So if Alice puts in a 1 rupee coin in her box, then her blue box pops out a toy car. That's basically rule number 1. Okay. Good. So far, there is no issue with this. Now, remember that you can get a car and a doll only if both of them put 2 rupee coins. Okay. So which means, and in this case, there is already a car that Alice has generated. So anything that Bob does necessarily produces another car. Okay. Because it says that any other combination, it has to produce either 2 cars or 2 dolls. Now there was already 1 car, so it definitely produces another car. And now we have almost actually filled up the possibility space. The final thing is if Alice puts in a 2 pound, coin. So if Alice puts in a 2 pound coin and Bob also has put in a 2 pound coin, then it has to produce a car and a doll in any order. Okay. So then it produces a toy doll here. But now if I look at all the sort of 4 possibilities and I compare with the set of rules I have, I see a problem. The problem is that this thing is incorrect, right? Because here I have produced a toy doll and a toy car in the case when Bob puts in a 1 rupee coin and Alice puts in a 2 rupee coin. But this possibility, cannot happen because a car and a doll could have happened only if both of them were putting 2 rupee coins, and and any other combination was supposed to produce 2 cars and 2 dolls. Now, of course, I did one particular order in which I did things. Now, of course, you can go back and do this as an exercise where you can do this in any order you want. You can try all possibilities. what you will find is that at best, you can satisfy, at best you can satisfy 3 of these 4 conditions. You'll always find at least one such case which does not conform to the rules. Okay, so what that means is that the success rate is constrained by 75%, and this is exactly the analogous version of what John Bell was trying to do. He basically calculated using the local hidden variable theory. He actually calculated the correlations between the measurements, and he came up with an inequality, a set of inequalities there. And then the point is, if you actually try to compute similar correlations using entangled quantum states, you can actually do something better. Okay. Now, the fact that you can do something better, in fact, you can satisfy everything, or not necessarily everything. I mean, it's still not 100% in Bell's thought experiment, suggested that there is really quantum entanglement at play. So this is what John Bell was trying to do, and this was almost the sort of almost the last nail in the coffin for the local hidden variable theory. The reason I'm saying that it's almost the last nail is because at some stage we needed an experimental verification of this, which eventually did come. And when we finally had an experimental verification of Bell's inequalities, of course, Bell's inequalities were not demonstrated exactly in the form that Bell wrote. People wrote down slightly different variants of the Bell's inequalities, which basically had the same content. And then experiments were done, which showed that indeed the results that they got were inconsistent with the local hidden variable theory, but they were consistent with what entangled quantum states would give you. And then there was very little doubt remaining as to whether quantum entanglement is there or not. So that's what I wanted to sort of say about why and how entanglement came to be. And let me try to sort of briefly summarize this history. So of course, many of you probably recognize this extremely famous picture. This is from the Solvay conference in 1927. This is often called as one of the most important conferences in the history of physics. And you can basically see all the big wigs of quantum mechanics in this picture. Then in 1935, Einstein, Podolsky, and Rosen wrote their EPR paradox paper. In fact, Schrödinger also then wrote his paper about how it seemed that entanglement is needed, but Schrödinger was also not very happy with this, what Einstein called a spooky action at a distance. But then in 1964, John Bell came along and showed via his Bell's inequalities, via his thought experiment, that local hidden variable theory cannot be correct. It has to be entanglement at play. And then in 1972, we had an experiment by Friedman and Closure, which again sort of experimentally demonstrated one version of Bell's inequalities. And then sort of slightly moving forward in 1982, Alain Aspect did a set of experiments again showing that Bell's inequalities are indeed violated. And again, it's basically saying that local hidden variable theory is not what's at play, it's quantum entanglement at play. And in 1990, Greenberger, Michael Hahn, and Zeilinger did a thought experiment, which again, since then has been adapted into actual experiments, again showing the violation of Bell's inequalities. And many of you might actually remember that Closure, Alain Aspect, and Zeilinger got the Nobel Prize in Physics last year, precisely for doing experiments and showing that Bell's inequalities are indeed violated. And I think with that, we can sort of put the local hidden variable theory to rest and sort of welcome this notion of quantum entanglement and actually make significant and serious mathematical statements about quantum entanglement. Okay. All right. So this is probably a good halting point, because I will now start actually talking about how do you quantify entanglement, because so far entanglement in our minds has been, or in what I have said, it has been an idea. But of course, we would like to put numbers to it. So if there are any pressing questions, I'll be more than happy to take them right now.
I have a question.
Sure.
The Bell's inequality. What is the inequality like? Is it about the success rate or?
No, so the Bell's inequality is about, so what you do is, so you imagine that there is a theory like this, that you have some quantum state, which, and you should have assumed that entanglement is not real, but you have some local hidden variables. And then you do many different kinds of measurements on these qubits. Because, for example, qubits are basically quantum versions of spins. So, for example, you can measure the Z component of one qubit and the X component of another qubit and so on. So there are different possibilities of doing measurements. So what Bell showed was that these measurement outcomes, if local hidden variable theory is correct, these measurement outcomes are correlated, and those correlations have some constraints. Okay, so I don't want to write that mathematically because that involves.
Thank you. Yeah, that clarifies.
Yeah, so that's the point, that the measurements are correlated, and those correlations have some inequalities or constraints.
So, Professor, there is one question by Hardeep. He has asked, can you explicitly define a measurement?
Yes, I can define a measurement, and please hold on to that question, and I hope I'll give you a very precise definition of a measurement in 10 to 15 minutes, but let me nevertheless go back and say what is a measurement. Okay, so let me so let me go here. Okay, this is the slide. So suppose I have a state here. Okay, now this is a coherent superposition of this qubit being up and the qubit being down. So what does measurement mean? You basically want to know, so suppose this was a classical bit. Okay, so you had only 0 or 1. So a measurement in that case would have given you either 0 or 1, depending on what that qubit was at that point of time. Now, quantum mechanically, you cannot say that this qubit was either 0 or 1 at any point of time. It's some superposition of the two. So what measurement does is you're asking the question that whether it's up or down, but the state is not neither up nor down. It's basically Schrodinger's cat type statement. So what actually happens is when you make the measurement, then the state becomes either 0 or 1. And this happens with a probability, like 0 happens with a probability C down square, 1 happens with a probability C up square. So the technical term we often use is that you take the state and project it onto one of the classical spin configurations. And the fact that this is a probability basically means that if you say do it many number of times, then C down square times the number of times you tried, you will get down. C up square times the number of times you tried, you will get up. Okay, so that's basically what a measurement here is. So that's why in quantum mechanics, these measurements often go hand in hand with the statement about the collapse of the state. Okay, so let me go on and try to start quantifying and trying to put some numbers on entanglement. So in the beginning, I said that one of the sort of physical notions of entanglement is that each part of the system has some information about every other part. Okay, so what that means is, suppose I take this big system and I chop it up into half and I take these two parts away from each other. So if I take this upper part away from the lower part, then what I'm doing is, if the states are entangled, then what I'm doing is I'm also taking away some amount of information of this lower part. And that basically gives me some extra uncertainty or randomness in the state of the remaining subsystem that I have here. Okay, so that's basically putting this in words. And the fact that we have some uncertainty or some randomness immediately brings to mind the term entropy. Okay, because we often sort of associate some randomness or the absence of knowledge with entropy. So what we actually want to compute is entropy of entanglement. That's at least going to be one. Of course, this is not a unique measure of entanglement, but this is one measure of entanglement, and we call it the entropy of entanglement. And in a way, it's not very surprising, because even if you go away from quantum mechanics, entropy and information actually have a very intimate connection, right? Because Claude Shannon, who is often called the father of information theory, he had this idea that you can define the information content of set of random variables in terms of what we call the Shannon entropy. So the idea is very simple. What you say is that suppose you have some random variable x, and that can take different values, x1, x2, and so on, xn, each with some probability p of x1, p of x2, and so on. So he defined the entropy as minus the sum over all the p's multiplied by their logs. And one way of sort of understanding this is what Shannon said was that if, let's say that there are some numbers here which are very highly likely, and there are some numbers which are very sort of unlikely. So if you now choose a random number from this particular set, and if you get a number which is very, very highly likely, then you would say that, well, yeah, I didn't really get much information. I was anyway expecting that to happen. On the other hand, if you get a random number which is very unlikely, then you'll say, oh, I didn't really expect that. So that's like a lot of information for you, because that brings in the amount of surprise, that something new information, because it's not something you were expecting. So this minus log of p, you can write as 1 over the log of p, and which of course is very large if p is very small. So then he said that, log of 1 over p is basically the amount of information each random number has. And then he summed it up with the probability of getting that. So that's basically the content of Shannon entropy. Now, there is an exact quantum mechanical version of this, which we call the von Neumann entropy. So if you remember, towards the beginning of the talk, I introduced this notion of the density matrix of a state, where the diagonal entries were basically the classical probabilities of finding the state in different configurations possible, and the off-diagonal entries basically contained the information about the quantum coherences. So exactly so think of this rho as some composite set of probabilities for finding the state in different possible, or think of this as a matrix which contains various combinations of the probabilities in which you can find the state in. So then there is an exact analogous formula for the von Neumann entropy for a given density matrix, which is, the trace is basically the sum over the diagonals of rho log rho, which is nothing but sum over p log p. And as I said, you can the reason you want to trace is because you want to look at all possible classical probabilities. But of course, it's a bit more than that, because you are not just summing over the diagonal entries of the given row, you're also summing over the diagonal entries of this matrix times the log of this matrix, which of course is a bit more complicated than simply summing over the diagonals. Okay, but let me try to motivate this quantity a bit better with some very simple examples. So let's say that I have a state with 2 qubits, okay? And I'll write the state as some coherent superposition of up-down and down-up, each with a coefficient C1 and C2. Now, of course, I can write down the density matrix in this fashion. And again, if you don't believe this, of course, you should go back and check. But if you write this, you'll find that the density matrix looks like this. Okay. So this is the density matrix, or a description of the state of these 2 qubits put together. What we now want to do, remember what we were trying to do here was we were trying to cut the system into 2 parts and take one away from the other. So that's what we want to do here. We want to remove the second qubit. Now, for some of the experts in the talk, that is mathematically equivalent to partially tracing over rho. What does that mean? You basically take this density matrix and you look for rows and columns where the second qubit has the same configuration. Okay. For example, this element is one such element because the second qubit here is down and here it's also down. So you take this and you put this on the top. Notice that this entire row is ruled out because although you had an up here and an up here and up here and another up here, these are 0. So for example, you can take this particular entry. You notice that the second qubit here is up and the second qubit here is down. So that's not a kind of matrix element you want. So you throw this out. And you go through this entire process And that's how you generate what we call the reduced density matrix for the first qubit. So basically, physically what I did was I had the full state of my system of 2 qubits. I wrote it as a density matrix, and I removed the second qubit. And once I remove the second qubit, the state that I am left with for the first qubit has a density matrix of this form. And now once I have this, I can go back to von Neumann's formula and compute the entanglement entropy, and I get this number, which in general is going to be finite. Okay, so this is what, for example, an entangled state of 2 qubits looks like. But now you can also ask that, okay, what does an unentangled state look like? An unentangled state typically would be something like this. See, it's a bit different from what I wrote before. Here I have the first qubit in some superposition state times the second qubit in the up state. So it's exactly like what I have done is I have taken the first qubit in some superposition state, and I have simply taken the second qubit in the up state and placed next to it. It's not important that it's in this, it's in the up state. This could also have been in some superposition state. That's not important here. The important thing is I can factorize my state into a state for the first qubit times a state for the second qubit. That is not something that I could have done here. There is no way of writing this state as a state for the first qubit times a state for the second qubit. Okay, so that's the crucial difference between the two kinds of states I wrote. So again, you can go through the same exercise. You can write down the density matrix for this full system, and then you can remove the second qubit. This is mathematically equivalent to sort of partially tracing over the second qubit. And now what happens is you end up with a density matrix for the first qubit, which looks like this, the reduced density matrix. It's a bit different from this. So notice that here in the entangled case, the off-diagonal matrix elements were 0. Here, the off-diagonal matrix elements are non-zero. Yet, if you do this calculation, you will find that the entropy of entanglement actually vanishes. Because what actually happened here was, in this case, the state was entangled. So as soon as you removed the second qubit, you made these off-diagonal matrix elements 0. Physically, that means that you removed the information of quantum coherences from the first qubit. So that's what this thing is about, that as I removed the second qubit, I removed a part of the information about the first qubit. In this case, I removed the information of the quantum coherences. And that's why I get a finite entropy of entanglement. In this case, just because I constructed the state in this way, even if I remove the second qubit, nothing really changes in the first qubit. It still retains all its quantum coherences, and there is no entropy of entanglement. Okay, so this entropy of entanglement is what we will use to quantify entanglement. And here is basically a couple of very toy examples of how you go about calculating it, and what kind of states give you entanglement, what kind of states don't give you entanglement. Okay, so the point is, to summarize this, that for entanglement to be there, what we need is a non-trivial superposition of many body states. So this is a non-trivial superposition of two qubit states. So this is a 2 qubit state, this is a 2 qubit state, and there is a non-trivial superposition of them. This gives me some non-trivial or finite entanglement entropy. Here, sort of in a fake fashion, it looks like a non-trivial superposition between the up and the down state, but it's actually not a non-trivial superposition, because I can take that superposition and factorize in this. I've written this in the factorized way. And in that case, of course, as we showed in the previous slide, you do not actually get any entanglement entropy. Okay, so with the notion of entanglement entropy as a quantifier for entanglement, what we will do is we will try to describe the dynamics of this quantity. But again, before that, I think before we get on to the dynamics of this quantity, I can probably stop and take a couple of questions if there are any important ones at the moment. Are there?
There are some.
Okay, maybe let me quickly go through the questions. So, okay, so I think there is one question I think I think I can answer immediately, which is what is the key difference between Shannon entropy and von Neumann entropy? I think that's an interesting question. So the von Neumann entropy is basically the quantum mechanical version of the Shannon entropy. So Shannon entropy is defined for classical probabilities and classical variables. So basically, this P's there are basically the probabilities. Now, a density matrix immediately is not a vector of probabilities, right? It is a matrix. Once you write down the density matrix in a diagonalized form, so you take this density matrix and diagonalize it in the way that you have removed all the off-diagonal matrix elements by doing a transformation, then there is no difference between the Shannon entropy of that diagonalized density matrix, because once you have diagonalized it, you can take the diagonal of that and treat it as a vector of probabilities in some different basis and calculate the Shannon entropy of that. You will basically get the von Neumann entropy. Okay. And I think that's related to this other question, that what's the reason behind using the density matrix instead of probabilities in von Neumann entropy? Because entanglement needs to carry information of whatever quantum coherences were present or not present. So you have to work with the density matrix. Of course, you are free to work with the diagonal form of the density matrix. So you take the density matrix, you diagonalize it, and then of course you can calculate the Shannon entropy, or you can calculate the Shannon entropy using the diagonal elements of the density matrix, which are nothing but probabilities. Okay. Okay, and I think I'll take one more question, and the rest of the questions I'll come back at the very end. So there's a question which says, could you explain quantum coherences? Yes, so quantum coherences basically means that, okay, a physical way of understanding this is that all the amplitudes that we write can be complex numbers, okay? So these complex numbers have a magnitude and have a phase. So this phase, again, is something that you can think of as it rotates, right? So if suppose what you do is, suppose two things are rotating in phase, in the sense that, they're rotating at, in sort of at the same rate, then we often call them coherent rotations. But if they're sort of rotating randomly, then the information of that phase can average out to 0. And that's when we call it to be incoherent. That's basically the idea. So the fact that a quantum mechanical evolution keeps track not of probability densities, but of probability amplitudes is what I mean by quantum coherences. Okay. And okay, and I think there is one last question which says, why does quantum entanglement exist, and what is the reason behind it? So that's what I was trying to motivate in the first part of the talk, that quantum entanglement is a property which is sort of inherent to quantum mechanics. Okay. All right. So let me, in the interest of time, let me go ahead, and we can of course come back to questions at the very end. So okay. So what I said is that in order to have entanglement, in order to have finite entanglement, I need the state to be a non-trivial superposition. And when I say non-trivial, I basically mean that I should not be able to factorize it into a state of the first qubit times a state of the second qubit. But as it turns out, these kinds of superpositions are extremely easy to generate with Schrödinger evolution. So what do we mean by Schrödinger evolution? So as we know that quantum mechanics, just like classical mechanics at the most microscopic scales are basically described by Newton's laws of motion, quantum mechanics is described by the Schrödinger equation, which basically says that IH bar del del t, or the time derivative of this state, is basically equal to an operator, which we call the Hamiltonian operator. But this Hamiltonian operator is nothing but the operator which corresponds to the energy of the system times, or that operator acting on the state. And the reason it's like this is because you may know from some old thing that you might have studied about Heisenberg uncertainty principles, that energy and time are conjugate or sort of conjugate to each other. So that's why in the time derivative of the state, the Hamiltonian or the energy operator appears. Now, what ends up happening is that if you try to solve this differential equation, you can immediately write, so we'll ignore this h bar factor from now. We'll sort of imagine that the h bar is always there. We are measuring time in units of h bar. So I'll not write h bar in the following. So if you try to solve this equation, you will find that the state at some time t is basically given by the exponential of this Hamiltonian operator times the time acting on the initial state. And as it turns out, this kind of operators, we'll call them U of t. These are what are called unitary operators. Okay, they are unitary because if I take this operator and multiply it with the conjugate transpose of this operator, I basically get identity, because that effectively physically means that U of t corresponds to some evolution in forward time. U dagger of t or U of minus t corresponds to evolution in backward time. So if I evolve forward in time from psi 0 to psi t, and then I evolve backward in time, I should basically come back to psi 0, which means that U of t times U of minus t should be identity. Okay. Now, in general, if I have some complicated Hamiltonian, as you can imagine, the exponential of that matrix, so the exponential of this operator is going to be some very complicated operator. So what that means is, if I start with a very simple state, so imagine I start with a state which is sort of down up, which means that if I write that state as a vector, this is up up, this is up down, this is down up, and this is down down. All of them are basically 0 because my state is in down up. So the down up state, or the entry corresponding to the down up state, has a 1 here. So I take this vector, I operate with this or multiply this operator from the left, which corresponds to a matrix multiplication. I will in principle generate some non-trivial set of amplitudes here. And what that means is I will basically entangle, I will put each qubit in some superposition and I will entangle them. That basically means that it goes into a non-trivial superposition of all the 4 possible states. So how do I actually understand this? So basically what happened was that pictorially, I had these 2 qubits in some state down up. I applied this operator and then it became basically entangled. Now, one way in which you can think about sort of as a measure of entanglement is, because I put this operator here, I put this box here, this got entangled. Now, every time, so what that means is that every time I put a box, it gets a bit more entangled, right? So if I suppose I had another qubit here and I put a box between the second qubit and the third qubit, then that would have entangled the second qubit with the third qubit and so on and so forth. So if you want to say, or if you want to ask the question that how much entanglement is there in this state, you can say that, well, one sort of very coarse-grained or sort of a very vague estimate would be that how many of these lines you need to cut, okay? Because once you put this gate, this became entangled. So if you somehow manage to cut this, then basically you have again disentangled the system. So the number of lines you need to cut is a measure of the entanglement, okay? So now let's try to think about this in a more complicated setting. So here I started with a very simple example of 2 qubits. Imagine now I have many such qubits and each of them are undergoing their evolution. And let me take some time evolution protocol where I'm randomly selecting any 2 nearby qubits and putting this box between them. So basically any box entangles these 2 qubits a bit more. So now you can, and I evolve it for some time t. So think of this horizontal direction as my arrangement of qubits in space and think of this vertical direction as time. So now I want to ask the question that what is the entanglement between this part of the system, which I'm calling subsystem A, and this part of the system, which I'm calling subsystem B. So let's look at the analogy drawn here. So what we want to do is we want to make a cut like this, which separates the two parts of the system, but does not cut through any of the boxes. So here is one possible way of doing this. Okay, so I do this, I follow this red line. You notice that it actually does not go through any of the boxes, yet it cuts through all the legs that are needed to separate the left or this subsystem A from subsystem B. Okay, so now what you can say is that the entanglement is definitely less than the number of legs the red string has to cut. Because of course, I could have been very inefficient and I could have made this string arbitrarily long, and I could have made this string wander all the way here, cut many links and then many legs and then come back again, which would have been unnecessary. So what that tells me is that if I draw such a string and I count the number of legs it cuts, the entanglement is bounded from above by that number, the number of legs I cut. So if you really want the best estimate of entanglement, what you should ask is not how many legs the string has to cut. You should ask that what is the minimum number of legs the string has to cut so that it separates the two subsystems. Okay. And if you think a bit about it, if these gates are there at regular intervals, then you can sort of imagine that one possibility would be to try to make a straight cut down the straight cut like this. And every time you find a unitary, you kind of go around this unitary in this way. Okay, so if you follow my cursor, you do this, and again you find another unitary. So you come back and again you do this. So basically you wiggle this red string around each unitary. But on an average, if I'm doing the evolution for time t, then I can say that the number of boxes that I actually find on this way is also proportional to time. What that means is that the number of legs I have to cut also is going to grow linearly with time. And that's exactly what you see. If you do a full-blown calculation of a quantum mechanical system, which of course I don't have the time to do here, what you do see is indeed the entanglement between these two parts of the system actually grows linearly with time in general. And this is actually quite a strong result, because it was never obvious when people started thinking about this, that how should the entanglement between two parts of the system grow. But sort of thinking about it in this language sort of makes it somewhat easy to understand that why this entanglement has to grow linearly with time in general. Okay, but this is not the full story, because in quantum mechanics, we have these unitary evolutions, but we also do quantum mechanical measurements, right? And measurements actually, in terms of entanglement, are basically an enemy of unitary dynamics. So let me try to explain why that might be the case. Okay, so suppose I play this game that I start with some simple state. I apply this unitary box and I get a state which is entangled. It's some superposition of all the four possible states. And let's say that this state has some finite entanglement. Now what I do is I go and do a measurement on just one qubit. Okay. Now, if you go back to what we discussed about how measurements work, the measurement is going to project, or measurement is going to select the states in which the second qubit is either necessarily up or it's necessarily down. Okay. Now, in this case, let's imagine that I do a measurement and I find, and I mean, it selects up or down depending on some probability. So in a given run of the experiment, let's say that the second qubit gets projected down. Okay. So if it gets projected down, then what happens is that all the component or all these coefficients where the second spin was pointing up gets set to 0. And then the state begins to look like this, modulo some normalization. Okay. So, what happens is that this factor goes away and this factor goes away. But notice that I'm left with this C up down times up down and C down down times down down. These are the two sort of components that I am left with. Once I write them out in this fashion, I can very easily factorize it, right? I can write this as a superposition state of the first qubit times a product with the second qubit. And we discussed that exactly these kinds of states where you can factorize them are completely unentangled. So what actually happened here was that all the entanglement got lost. Whatever entanglement that had gotten generated by this box basically got lost once we did the measurement. So the moral of the story is measurements try to destroy the entanglement. So again, going back to this geometrical picture, what you can say is that once you do a measurement, that's effectively equivalent to putting a cut in this line. You see that I've made this gray line broken. And what that then means is that you can take this red string and make it go through this broken line. It does not cost anything. You are not actually cutting any leg. So of course, the entanglement is actually 0. So let's now translate this again to a more complicated setting where I have my boxes which generate entanglement, but I also have measurements. So each yellow box here is basically one such measurement. Okay. And let's say that I have P measurements per unit time, per unit length in my system. So think of this as some density of measurements or some rate of measurements. Now, what we want to do is we want to go back to this geometrical picture. So the point is the following, that I can replace each of these measurement boxes with a broken line. And what that means is I can try to find an optimal path where my string, this red string, actually goes through as many of the broken lines as possible. Because I know that the broken lines don't cost me anything. So what that means is that by putting these broken legs, the measurement has reduced the number of legs that the string has to now come and cut, the red string. So that naturally means that the entanglement in the state is very low now compared to what it was before. So that sort of suggests that measurements actually suppress the entanglement growth in time. So here, of course, I have drawn a very fine-tuned situation where I basically put the measurements at locations where I could actually make this red string go through all broken lines and remove the subsystem A from subsystem B. And this is a case where basically, even though I have so many of these boxes, the entanglement between the two subsystems is actually 0. So now you see why I said that why measurements are an enemy of unitary dynamics as far as entanglement is concerned. Okay. So now the question that arises is, if I now change this, P, which is the number of measurements per unit time per unit length, does something drastic happen? Because quite often in physics, we see that if there are two competing effects, then very rich physics emerges, right? Because suppose one of the classic examples is, say, if you have some magnet, let's say, and it's a ferromagnet. So the energy cost is very high if your magnetic domains are not aligned with each other. In that case, what happens is that if your temperature is very low, then the energy minimization tells you that all the magnetic domains will align and you will get something which we call a ferromagnet. But then if the temperature is very high, then it is trying to excite the domains and make them random. And then there is a competition between this ferromagnetic coupling and the temperature to give something. And quite often in this case, we see what we call a phase transition. And when I say a phase transition, what I mean is that something very sharp and non-analytic happens at the phase transition. In the analogy that I gave, the ferromagnetic order completely goes away. The system goes from a ferromagnetic state to a paramagnetic state, and these are completely different things. And this happens in a very abrupt fashion. So this competition between these unitary dynamics brought about by these boxes and the measurements, then it's a natural question to ask that whether this competition can give you some phase transition or not. And the answer is yes. But before I go to that phase transition, let me make a small digression. And it's about this phenomena of percolation. And this percolation is basically a classic problem in statistical mechanics. And it's it's such a powerful problem that by just studying the percolation problem, you can learn a lot about statistical mechanics and how many particles with many systems or many how systems with many particles or many degrees of freedom act collectively. So the problem is very simple. It's actually deceptively simple. What you ask is, suppose you have a square lattice, like I have drawn here, you tilt it. I mean, the tilting is just for convenience, you don't have to tilt it. So suppose you have a square lattice. Now you had these links on the square lattice. Now with some probability p, you start removing them. So what you do is you go to each link and with some probability p, you remove it. And now you ask the question that what is the probability that there is a cluster of connected sites that span the system? So suppose, here the picture basically means that all these solid lines are links that are present and all these dotted lines are links that are not present. So you start from one end of the system and you basically start following all the connected lines and you grow this cluster. And you ask that if I start from one end of the system, can I actually get to the other end of the system? And this is an example where you can. But imagine what happens if you start removing too many of the links. There's a possibility that you will close off or you will cut off all the paths that go from one end of the system to another end of the system. And now, you can do this computation. Either you can simulate this or you can calculate many things on a piece of paper. And what you find is that if you plot the probability of there being a cluster of connected sites that span the system, it basically looks something like this. So when p is very low, you have removed very few bonds. So you have a finite probability that you have a cluster that spans the entire system. Whereas beyond some critical value, which we call PC, what ends up happening is that the probability that you have such a spanning cluster goes to 0. Now, this function is finite for p less than pc and 0 for p greater than pc. So obviously, this function cannot be an analytic function. It cannot be a smooth function. And that tells you that something very special happens at this point pc, which is nothing but a phase transition between a percolating phase and a non-percolating phase. Now, why did I give this particular example? I mean, why did I choose this example to demonstrate phase transition? Because our competition between the unitary boxes which were generating entanglement and the measurements actually look very similar. Because remember what these measurements were doing, but they were removing some links. They were removing these legs from this picture, which of course is not a regular lattice like a square lattice, but pretend that this is some kind of a lattice. These are some links on that lattice. And what the measurements are doing is they're removing these, or they're removing with some probability p, they're removing these links or breaking these links or breaking the legs. So now you can ask the question that suppose I have a system where I have a set of unitary boxes and I have a set of measurements. Then remember that in order to have some entanglement, I need to have a situation where this red string cuts some legs. But if it so happens that this red string does not need to cut a leg, okay, in that case, what it means is that the entanglement has gone to 0, but that's also saying that there is no connection between the left half of the system and the right half of the system, or there is no connection between subsystem A and subsystem B. So that is exactly equivalent to asking the question that is there a cluster of connected, let's think of these blocks. Is there a connected cluster which starts off from the left half of the system and is able to reach the right half of the system? And for example, in this particular instance that I have drawn, the answer is clearly no, because what you can see is you can take whatever is to the left of this, whatever is to the left of this red string and pull it apart. And basically that part is completely detached from the right half of the system. Okay. So this problem looks exactly like that of a percolation problem. It looks exactly like a percolation transition, or one expects a percolation transition here. Now, whether the nature of this transition is the same as that of a percolation transition is a much more subtle question. But what this tells you is that there is definitely a phase transition in the system. where in one phase, when the measurements rate is small enough, you have a lot of links that or a lot of legs that this red string needs to cut, which basically means that in that phase, there's a lot of entanglement in the system. And there is another phase, which is analogous to the non-percolating phase, where the links are, or you basically have to cut very few, or the red string has to cut very few links or no links at all to separate the two subsystems, which is basically the phase where there is very little entanglement. And sure enough, if you try to sort of solve this problem, again, I don't have the time to discuss how do you solve this problem, you actually find that as a function of this measurement rate, there are indeed two phases, okay? In one phase, which is the low measurement rate phase, the entanglement keeps growing linearly with time for the reasons that we explained in the for the same reason that I gave in the context of the case with no measurements. So there is one phase where this entanglement keeps growing linearly with time. On the other hand, there is another phase where the system is disentangled, meaning that this entanglement growth, it grows for some time initially, and then it saturates to some finite value. And you might as well ask that, why is there a finite saturation? Well, there's a finite saturation because it might happen that the two parts of the system are not completely disconnected from each other, but there are a few remaining links which the red string needs to cut. And that's all you need to do to separate the two parts. And that's why you get some finite and small entanglement. So now these two are very drastic, or these two temporal entanglement growths are very drastically different. In one case, it keeps growing unbounded linearly. In another case, it grows for some time and then saturates. And indeed, what happens is that there is a sharp threshold where this phase transition happens. But now this phase transition is not in the property of the, so in this phase transition is not a property of some equilibrium state. This phase transition is a transition in the nature of the dynamics, in the nature of the quantum dynamics in the two phases. So that's why this is a dynamical phase transition in entanglement growth. So now I think I'm very close to the end of the talk. So let me try to start wrapping up. So what did we basically learn? We started off with motivating why entanglement has to be. Then we sort of tried to put some numbers on entanglement, or rather come up with some quantitative ways of, or ways of quantifying entanglement. And then finally I said, or what I sort of seem to have said is that the two major players in any quantum dynamics, namely Schrödinger evolution and measurements, they actually have completely different effects on the entanglement. And the competition between them is very interesting and it's very rich because it actually gives you two different kinds of phases. And having two different kinds of phases which are drastically different is always of extreme importance, because possibly you can use them to do something useful, because you can start asking questions like, if there is a lot of entanglement in the system, then it means that the correlations in the system are very non-local. Each part of the system is very strongly talking to some other part of the system. Now, this can be good for some cases, because, some of the cases where this kind of a feature is very good is when we want, let's say, when you want to, very sort of vaguely speaking, when you want to hide some information, okay? So suppose I give you a quantum system where the information is actually hidden in these very, very non-local faraway correlations. Then unless you know exactly what you are looking for, it will be very difficult for you to find what that information is. On the other hand, the problem with these kinds of phases is exactly this, that if you want to use these kinds of phases to store, retrieve, manipulate quantum information, it becomes very difficult because every time you have to do some non-local process. On the other hand, phases like this, where the entanglement does not grow, what that means is that the correlations in the system remain very local. And one can say that, well, this is good. These can serve as good, possibly these can serve as good memories, because you started off in some state, the information did not spread out everywhere else. It sort of stayed where you put the information in. So it's like a good quantum mechanical memory. I mean, these are all very vague concepts, but these are things that people are indeed thinking about seriously. So you can say that this is a very good quantum memory, but of course, this is also a very fragile memory because all the information is very local. So if you actually go and disturb something locally, you can actually destroy the information. So what I'm trying to say from this is that it is of both sort of fundamental and theoretical importance to think about these things, as well as it's important to think about these things in sort of in light of all the experimental developments that are happening with companies like IBM and Google and several other startups actually building very small quantum computing devices, and where all of these issues actually become very real. Okay, so I think with that, I will try to end the talk. So the central point that I wanted to make was entanglement is one of the most important tenets of quantum mechanics, and you cannot understand quantum mechanics if you don't understand quantum entanglement. In fact, again, going back to Schrödinger, he said that I would not call that one, but rather the characteristic trait of quantum mechanics. So to one of the founding figures of quantum mechanics, entanglement is basically the characteristic trait of quantum mechanics. And I think that is probably the best advertisement for quantum entanglement that one can have. So I think with that, I will end the talk. I think I've said what I wanted to, and I'll be more than happy to take questions now. Yeah, thank you. Thank you for your attention.
Thank you so much, Sthitadhi, for this wonderful talk. And yeah, it made many concepts, it illuminated many concepts, and thank you so much. So now the floor is open for talk. Somebody was really asking about quantum information, so maybe you should answer that first. Somebody was asking many times. So
so okay, maybe I can go through some of the questions in the chat. So let me maybe start from the top maybe. Okay. So okay, so I think there is a question. Sorry, there are a few more even above that.
if you can club some of the questions that
yeah, I think that's what I'll then try to do. So okay, so I think there is a question which says how to measure quantum entanglement. So how to measure quantum entanglement? Okay, so it depends on what you exactly mean. Do you want to? Does the question mean that do you want to calculate quantum entanglement by doing a calculation or doing a calculation on a computer? Then basically, the answer was in the talk that you write down the state as a density matrix, you remove a part of the system, you are left with the reduced density matrix, and you basically diagonalize it and calculate the Shannon entropy. If you are asking how to measure quantum entanglement experimentally, that is, of course, one of the most challenging things, because unlike any physical observable, I mean, entanglement is not a linear operation on a quantum state. So normally, if you were to measure some quantum mechanical observable, you take the state, you operate on that state with the Hermitian or operator corresponding to that observable, and you get some answer out, you do statistics, and you find out the expectation value. Entanglement, there is nothing called an entanglement operator. So the way people calculate or measure or have been trying to measure entanglement in experiments is what they do is they say that yes, entanglement is basically some combination, some complicated combination of many non-local correlations. So there are experiments where people, where experimentalists try to measure all possible non-local correlations. This goes under the name of quantum state tomography. And it's called tomography because basically you have calculated all the correlations that a quantum state can have. So they measure these correlations, and then they put these correlations together to measure quantum entanglement. Okay, so then I think then there is a question about what is quantum information, how to calculate the information of any particles, how to calculate quantum information quantity. Yeah, so I think this goes back to this question that entanglement is possibly one measure of the quantum information contained in the system, because one way in which you understand about information is about the correlations present, and entanglement in that sense is quite a powerful thing because it contains all possible non-local correlations. So then I think there is a question about if the temperature is 0, the entropy is infinite. Why? So, okay, I mean, let me not try to get into thermodynamics, but this, as far as I understand, if I stick to, in this question, if you say entropy, if I say entanglement entropy, then the entanglement entropy in general is not a function of the temperature, it's a function of the state. Now, you can relate it by saying that if I give you a system and its state in a particular temperature is something, then you can compute the entanglement entropy of that particular state. Okay, then there was another question which says how it relates to basic ideas in quantum physics, such as loss of quantum coherence. So yeah, so loss of quantum coherence, okay, this is actually an interesting question, because indeed what happens is general quantum systems do not undergo the kind of unitary dynamics that I was talking about. There is always some noise, it's connected to some environment, and that actually does affect these let me go back to this slide, and that does affect these off-diagonal matrix elements. And if they are not exactly of this form, you don't have a coherent quantum state, and that's how quantum coherences get affected. Okay, then there's a statement which says if no hidden variables are there, then according to the experiment by Anton Zeilinger, doesn't it support the concept of? No, it doesn't, right? I mean, it just says that there are no hidden variables, but it says that you can have an entangled state. So the point is, why is this not faster than light communication, or why is it not faster than or not spooky action at a distance? Of course, one can give a very, very mathematically rigorous answer to this, but let me just say one thing, that suppose there is an entangled state with two qubits which live far away from each other, then if I measure something on one qubit, then somehow that information has to be transferred to the other qubit classically, right? So that's why I don't think it puts any, there is no issue with faster than light transmission of quantum information. So someone says, so essentially entropy is the average of information in the system. Yes, I would say that's roughly correct. I think I answered the question about the difference between Shannon and von Neumann entropies. I think I answered why are we using the density matrix. I answered, or I at least tried to motivate how you put in a measurement. There's a question which says non-trivial superposition. Yeah, so I explained what a non-trivial superposition of superposition means, that I should not be able to factorize the state. I think there's a question about what is the application of quantum entanglement. I briefly touched upon that at the end of my talk. There's a question from YouTube. It says, just as the evolution entangles the qubits, can it also disentangle them? So this is actually a very interesting question. So yes, so of course, suppose, and I think there is a related question there which says a unitary evolution is reversible. If the entanglement is generated via the unitary evolution, then it should be possible to reverse it. So of course, so if I do some unitary evolution and then I revert exactly the same evolution back in time, then I'm going to get back to the original unentangled state that I started with. So, but generally that does not happen, right? I mean, basically you have a system which undergoes some evolution according to some Hamiltonian or some property of that state. It's not in your hands to revert the evolution. But of course, yeah, unitary dynamics is indeed reversible. So if you could engineer a exact, precise, time-reversed operator, you could definitely undo all the entanglement. So then it says, does cutting means checking the entangled particles at a particular time? No. So the cutting idea that I was trying to present here was it's not something you do physically. Okay, it's basically a way of understanding the entanglement. It's like a probe. So or you think of it as a calculational tool to sort of think about how much entanglement is there in the system. So you see how much entanglement is there in the system when you try to take them apart. Okay. Okay, so then there is an interesting question which says that by measurement, do you mean random collapse of the state? If so, is it truly random? No, of course I mean a random collapse of the state, but the collapse happens with some probability, as I mentioned here. That suppose I start with this particular superposition state, I measure, I'll get down with probability C down square, I'll get up with probability C up square. So it's random, but the two random events have their own probabilities. Then it says, if we have an entangled system and we write the density matrix, then if we write some reduced density matrix for its subsystem, is it that we have unentangled system 1 from 2? No, the answer is no. You have not unentangled it. What you have done is you have thrown away one of the systems. And or you can think of it as you have averaged over all possible states of the system that you have thrown away, and you are left with some remaining state of the state of the remaining system. Okay. There is a question which says, what happens to an entangled system after the measurement? Whether it goes to a coherent superposition state or not. So no, it doesn't go to a coherent superposition state. It goes to a state which looks like a product of the two states. Because once I for example, this is a coherent superposition. Once I do the measurement, it goes to a state which is basically a product of the two states. So there's a question which says, can we say entanglement destroys the quantum coherence? So no, entanglement does not actually destroy quantum coherence. What it does is, so if a state is entangled, then what it does is, if you throw away one of the parts of the system, the remaining part of the system is no longer in a coherent state. So in order to get an incoherent state of a part of the system, you have to throw away, entanglement is not enough. You have to also throw away the other part of the system. So then there is a question which says, when one says measurement, it appears it is in the hand of the experiment. But from your talk, it appeared that the event of the measurement is not entirely in our hand. And that's true. I mean, that's basically a reflection of the probabilistic nature of quantum systems, that of course you can choose what you want to measure, but the outcome of the measurement is not entirely in your hands. There is a certain randomness to the outcome of the measurements, and that's what I was explaining here as well, that you choose to measure it, but whether you get up or down is not in your hands. It happens with its own probability. Okay, I think I have answered most of the questions that I can understand from the chat. So if there are questions from, so Anupam, if there are questions from YouTube, then
no, these are the questions.
Okay.
There's one last question from YouTube. So just now someone has put, I'll just copy and paste it. You can have a look.
Okay, so this is a question. I mean, of course, I'm not an expert on the foundations of quantum mechanics, but the reason that the reason that the Copenhagen interpretation is sort of what we study more often than not is because it seems to work for almost everything that we do. So whatever it predicts has rarely or has almost never been proven to be incorrect. So that's, I think, a good reason to sort of believe in it and study it and try to understand it. Okay, I think, yeah.
I think these are the only questions. Yes.
Okay.
So there are probably many more questions, but I think out of in view of time, so we should probably stop here now. Thanks, Sthitadhi, for this wonderful talk and for taking so many questions. Is it okay for them to ask you over email sometime?
Absolutely, yeah.
Okay, so you can ask your questions over email and.
I also could not take all the questions in the interest of time, but yeah, I think I answered the ones that I felt were the most sort of pressing.
Okay, thanks a ton.
Yeah, okay.
Thank you again.
Okay, thank you. Yeah.
Bye. Bye.